Hello, everybody. Welcome to the monthly fourth seminar. And we are very glad that we invite Professor Liebermann as an speaker of the fourth seminar, as a first speaker in 2025. So before he starts the presentation, I will show some update of the force. By the way, my name is Kyusei Tsuno, force research scientist, and I will lead this seminar instead of Dr. Kara Bragman. So first, we have several social media, and we have YouTube, and you guys can see the past seminars in 2023 and 2024. And we also have several social media like X and Instagram and LinkedIn. So that subscribe us and you guys can see the update of the force. Today, Professor Bob Lieberman will give a talk, and the next month, Professor Rebecca Fisher of the Harvard, and in April, Professor Asma Bolivar of the Western Washington University, and in May, Professor Damanvir Agrawal of the Arizona State University will give a talk. So, we have a little bit of the update about the force. So we have two multi-anvils, Ichiban 6,000 ton Kawai type press and the Jasmine 1,500 ton Vogen writers Osugi type press. And we are glad to announce that we successfully performed an experiment with the heating. So this picture shows Ichiban on the left side, the cell assembly with the tungsten 52 millimeter tungsten carbide cube before the pressurization. And the middle figure shows the experiment during heating. So in this picture, temperature is 1,000 degrees C. And the picture on the left shows the cell assembly after the experiment. So this is a picture of the Vogen writers press Jasmine. Left figure shows the cell assembly before the pressurization. And in the middle figure, this is during the heating at 5 meganewton. And the Eurotherm shows 544 degrees C, but target pressure, target temperature was at 1400 degrees C. And the right figure shows cell assembly after the experiment. So now Professor Bob Lieberman will give a talk, but before that, I will introduce Bob. And Professor Bob Lieberman got an bachelor at Caltech, and after that, he obtained a PhD in the Columbia University. After that, he spent 6 years in ANU working with Ted Ringgood. Then now he moved to the Stony Brook, and he served as an professor up till now. So Bob, you can start the talk. You can start a presentation.
Okay, thank you very much. I would like to thank Kara Brugman and Tsuno Sensei for the invitation to present this talk. I must tell you that it's been more than a decade since I've given a professional talk, and I think I still know how, but in the move from our house in September, where we had lived for 47 years, to an independent living community near Port Jefferson, New York, many items that I thought I had were not cannot be found. So I was searching for photographs and videos during the last few days. I also apologize. Apparently, I am not to be seen during this talk, which is okay. I did dress up in a suit coat and a proper shirt, but it's perhaps just as well you can't see me because I have a very scratchy voice due to some medical problems last year. And I've lost my notes. So let's just go ahead and see how this works. This is my title, Ultrasonic Measurements of Sound Velocities at High Pressures and Temperatures. Next slide. This is not a new field. A lot of the developments that took place in ultrasonics and sound velocity measurements occurred in the 60s after developments in various laboratories during World War II, including Bell Telephone Labs and the Massachusetts Institute of Technology. And most of you will recognize the names of other laboratories that measure sound velocities minerals, including Francis Birch and later Rick O'Connell at Harvard, Orson Anderson at Lamont, Gerhard Barsch, and later Buzz Graham at Penn State, Hartmut Spetzler at Caltech, then Colorado, and Gene Simmons at MIT. And the rest is in the abstract that I presented. So next slide, please. I'm going to propose to trace the development of ultrasonic techniques at ever-increasing pressures now reaching conditions of the lower mantle over the last 60 years. I've chosen to summarize this history with my personal perspective, starting with experiments I did as a graduate student at Lamont and extending to the most recent experiments in our high-pressure laboratory at Stony Brook. As many of you will be aware, many of the recent studies of sound velocities of minerals at high pressure temperatures are being conducted at the synchrotron X radiation facilities of the U.S. Department of Energy, including NSLS at Brookhaven and the APS at the Argonne National Laboratory. Next. I'm going to choose to dedicate this talk to Orson Anderson, my graduate supervisor, in whose memory we organized a book that was published last year and has 30 or 40 articles related to mineral physics. I have a copy to show you, but since I'm not showing a video, you can just use your imagination. Next slide, please. When I first came to Lamont in 1964, I was a seismology student, and I began to work with Paul Pomeroy and Jim Brune on developing seismic techniques to be able to discriminate between underground nuclear explosions and natural earthquakes. And this diagram, we discovered or developed a technique to discriminate these two types of seismic events using the measurements of the sound velocities on the vertical axis, the surface wave magnitudes on the vertical axis and the body wave magnitudes on the bottom. The line that says 1.59 MB minus 3.97 is an old Gutenberg Richter line that is supposed to represent natural earthquakes. The various dots are from underground nuclear explosions detonated by the United States, France, and the Soviet Union at various sites throughout their countries. And you can see that all of the dots lie below and distinctly beneath the earthquake line represented here. Tsuno, can you tell me if I use the pointer, does it show on the screen? Tsuno, are you there? Hello? Dr. Tsuno, can you hear me?
Sorry, I was muted. So this is the pointer. Yeah. I
I
can
can
hear you.
use the pointer,
Actually, I'm controlling the slide, so it
but
is
I have a pointer. Is it okay?
Yeah.
Okay.
Uh. Yeah.
Okay. Next slide. While I was a graduate student in seismology, Orson Anderson had been at the Bell Telephone Laboratories, and he wrote a proposal to the Department of Energy to do some acoustic work at Bell Telephone. Morris Ewing, the director of Lamont, was a member of the panel evaluating these proposals, and somewhat outside the bounds of what is normally accepted for confidential reviews, Ewing called up Orson and said, "Why don't you come to Lamont and do this work? I'll set you up in a laboratory that you can have on your own." So Anderson moved to Lamont in the early 60s. He began to teach mineralogy, and one of the classical geology faculty at Columbia said, "That's impossible. He's a physicist." So Orson said, "Well, what about all these other physicists like Dubai and Bragg and others who have contributed to mineralogy?" And at that point, the geology professor decided to be quiet. Orson was clever enough to recruit two young people to help him run the laboratory, Ed Schreiber from the Alfred College of Ceramics, and now here is Soga from Japan. Later on, he recruited me to his mineral physics group, but before he did that, he asked Soga to interview me and see if I would be a suitable member of the experimental group. So Soga asked me a couple of questions. He said, "When you were young, did you have a bicycle?" I said, "Yes." "What did you do when it broke?" "I fixed it by myself." And he said, "Did you ever play sports?" And I said, "Yes, I played intercollegiate football." "What position?" "I was quarterback." So Soga concluded from that interview that I knew how to fix things, and I also knew how to organize things. So as a quarterback has to do. So I got admitted to the Anderson group, and the first thing he did was saying, "I have a contract with the Air Force Office of Scientific Research, and I promised to write a review paper on sound velocities in rocks and minerals, but I don't have the time to do it. It's your job to do it." So the next slide shows the result of that effort. We wrote a several hundred-page report on sound velocities in rocks and minerals. I say we wrote it. I think I should say I wrote it. And it includes 95 pages of data at room temperatures and pressures, and as a function of pressure and a function of temperature for mineral and rock velocities. So it became a catalog of what was available up to that time. This paper was also incorporated in a volume by Warren Mason some years later. Next slide, please. Orson didn't know what to call his laboratory, so he decided to call it mineral physics. And Ed Schreiber made the sign that appeared on the outside door of their laboratory at Lamont. And that sign now is installed at the Mineral Physics Institute at Stony Brook. So it's passed from Orson to Ed to Ed's widow, Charlotte, and then subsequently to me. And it also helped to define the field, but nobody was quite sure what mineral physics meant. So Bob Hazen decided, of course, to step in, and the next slide, I think, shows what he decided. He said, "Mineral physics is the study of mineralogical problems through the application of condensed matter physics." Well, that's not quite true, because we use not only physics, but also solid state chemistry. And we study not only minerals, but all materials related to natural minerals. For example, structural analogs, glasses, melts, and fluids. And many of us consider Francis Birch to be the father of mineral physics, based on his seminal paper in 1952, summarizing the state of knowledge of the elasticity and constitution of the Earth's interior at that time. Birch never used the term mineral physics, and Orson claims that it was first used by Edvard Gruneisen, the German physicist. So Birch, in the early 1960s, measured velocities of an enormous number of rocks and minerals to 3 kilobars using pulse transmission. Gene Simmons later followed that up with measuring the shear wave velocities in the same suite of minerals, and that formed the basis of what was used. But other techniques have been developed at the Bell Telephone Laboratories by people like Hal McSkimmon and Warren Mason. Next slide. And of course, the object of these studies from the point of view of a geophysicist is to try to unravel the seismic models that give us velocity and density as a function of depth, and then invoke experimental petrology and the knowledge of phase equilibria and chemical composition, and finally use mineral physics to provide the code to unravel these results from seismology in terms of measurements of pressure, temperature, mineralogy, chemical composition, and even volatiles. Next slide. Over the next decade, in the 60s primarily, the Lamont group published more than 75 papers, both experimental and theoretical, in mineral physics. Most of the experimental studies were focused on using physical acoustics, not only for resonance ultrasound, but primarily the techniques of pulse superposition and phase comparison to measure pressures up to what seemed to be a large pressure then, 0.4 GPa or 4 kilobars, and temperatures about 500 K. The next slide. Of course, we don't do this work in isolation from other things in geochemistry and geophysics, and I like this slide that we often ascribe to Harry Green and Ann Lattimore that shows the connection of mineral physics to other disciplines of geosciences, including petrology, planetary science, seismology, geodynamics, geomagnetism, geochemistry, and even climate and material science. Next slide. So Anderson incorporated the ultrasonic techniques developed at Bell Labs, and basically it's just a question of imposing different reflections of the sample and other interfaces. So you have a piezoelectric transducer of the kinds that were developed during the war to generate an acoustic signal that travels through a buffer rod, reflects off that buffer rod's specimen interface, extends into the sample, reflects off the sample or specimen air interface, and returns. So you have, as you look at it on the oscilloscope, a series of echoes, both the input signal, the echo from the buffer rod, the echo from the specimen, and of course the difference between these two tells you the travel time in the specimen itself. It doesn't tell you the velocity, it tells you the travel time. The next slide is the first experiments I did using this technique. I measured the frequencies of both compressional and shear waves as a function of pressure to 3 kilobars, 0.3 GPa for hematite at room temperature. Now, these measurements were done in a liquid medium apparatus, and of course, we had no idea how to measure the change of length. But Cook had developed the technique some years before, which is summarized in these equations, that allows you to use the travel times for, the travel times for both compressional and shear waves and combine them to give you the length changes that occur across this pressure regime, but still only at room temperature and only a direct measurement of length. The next slide, I think. This is a for the geologists in the audience, Orson Anderson was a native of Utah, and he loved the areas of southwest Utah and northeastern Arizona. So he took our group on field trips to the diatremes in that area in 66 and 67. Here is a Kenny, sorry, I forgot his last name, rowing Soga and Anderson down the river toward a kimberlite pipe or diatreme. This is Mule Ear. And a little bit later on, I climbed Mule Ear and was able to map this dike that radiates from it. So this was our experience in doing that. And of course, the group was a little strange. If I have the next slide, you'll see why I say that. This is a photograph looking at an outcrop at the Mule Ear diatreme with Gene Shoemaker, the prominent geologist, showing off this outcrop to Ed Schreiber, a ceramist, Hiro Soga, a glass technologist, Orson Anderson, a solid-state physicist, and even Peter Molnar, a very young Peter Molnar, as a seismologist. So it was sometimes it was expressed as the being leading the uninformed into nirvana. Next slide. One of the things we did in our laboratory was to combine ultrasonics and combine it with a multi-anvil apparatus that we had developed and I'm sorry, not developed, but purchased and imported from Japan in the 1970s, I guess, and maybe in the 1980s. I'm sorry, this is a terrible slide, but basically inside the compression of the anvils, much the way Tsuno Sensei showed you the massive apparatus at ASU in his introduction, it compresses these cubes. On the back of one of the cubes, we mount a transducer, and that transducer generates an acoustic wave that travels through a buffer rod. At the interface with the sample, it has a echo. It travels through the sample, generates another echo, and the difference of those two, of course, is the travel time within the sample. Still no measurement of length directly, but it allowed these experiments to be done at pressures up to 5 to 10 GPa. The next slide. Sorry, I'm a little bit out of line because I can't see the whole slides. One of our graduate students, Shubing Wang, did a very clever thing in the laboratory of Baosheng Li a few years ago. She decided to use polycrystalline alumina and measure its wave velocities as a function of pressure as a sensor. So we had within the sample chamber, this octahedral arrangement, we had a pressure standard so that the transducer would transmit the acoustic wave through the anvil into the acoustic buffer rod, the alumina in and out of the sample. And so we had a more direct measurement of the pressure within the sample chamber. I think the next slide will show some results of that work. Yes. This is cell pressure as calibrated versus oil pressure. The triangles are the data from the alumina experiment up to 12 GPa, and you can see that they compare very well with the standard transitions that we know from previous work in bismuth and zinc telluride, so that instead of having just a few fixed points, we have a continuous measurement of pressure within the sample chamber. Next slide. So one of the things we needed to do, we have a technique to measure the sound velocities, but we needed some specimens. And as part of his PhD research, Gabriel Guanmisia developed and adapted some of the hot pressing techniques that Ringwood had taught me in Australia to be used in our high pressure apparatus at Stony Brook. And then those hot pressed polycrystalline specimens were used by ultrasonic interferometry to measure the sound velocities, in his case, for his thesis in the high pressure forms of forsterite, Wadsleyite, and ringwoodite. Later in the laboratory of when Sally Rigdon worked in Jackson's laboratory, she used a piston cylinder apparatus to use the high pressure measurements in some of the specimens that were hot pressed by our team at Stony Brook, and also had hot pressed at the ANU in the 70s. The next slide. Excuse me, I need a drink of water. And again, I apologize because my slides are out of order and all my notes are submerged, and in addition to my scratchy throat. It was really work by Jackson Niesler and Don Widener, who developed a procedure to correct the elastic wave times measured by ultrasonic interferometry for the phase shifts arising from the propagation of these waves through the thin bond coupling to the crystal. And they applied this in a 3 GPa liquid medium apparatus of the kind that was originally developed by George Kennedy at UCLA. And then we bought the ANU interferometer and installed it at Stony Brook. And I think the next slide is going to show some of that. Could I have the next slide, please, Suno? Yes. This collaboration with ANU was done by my colleague, former graduate student, now colleague Baosheng Li, and former graduate student, now professor at Delaware State, Gabriel Guanmisia. This is a young Bob Liebermann back in 1991 with Gabriel and Sally Rigdon from Jackson's laboratory, making some measurements at Stony Brook while in the multi-anvil apparatus. Just a footnote for some of you who may know Yuri Litvin from Chernigolovka. He's up here mounting a specimen inside the big split sphere apparatus. So Jackson actually came to Stony Brook for a few months, and with Baosheng incorporated the Jackson ultrasonic the ultrasonic approach developed by Jackson and his colleagues into our multi-anvil apparatus at Stony Brook. We call this a Kennedy press because it was originally one of the ones that was in George Kennedy's laboratory, was bought by the chemistry department at Stony Brook, and we took it out of surplus and installed a Walker-type high-pressure module inside it. Next slide. So Gabriel also, as part of his PhD, went to Australia and with Sally Rigdon and worked with their interferometer to get familiar with it, and took some of his polycrystalline specimens that he made, as well as some of the ones that I had made back in the 70s, and they were able to measure these velocities up to 3 GPa in Ian Jackson's laboratory. The next slide. We also were interested in how these wave velocities varied with temperature, and in the laboratory of Jackson at ANU is a high temperature ultrasonic apparatus, and Jennifer Kung, as part of her doctoral studies, came to Stony Brook to make synthesize polycrystalline specimens of scandium aluminate perovskite, and then took these back to her laboratory in Australia and measured the temperature dependence. She also did that with the high temperature velocities of orthoenstatite back in Jackson's laboratory. So we have both approaches to measure extremely high temperature in the laboratory at ANU, and also high pressure at our laboratory at Stony Brook. Next slide. Okay. As I mentioned before, Jackson spent 6 weeks in Stony Brook helping Baosheng interface his ultrasonic interferometry with the 1,000-ton split cylinder apparatus of what I call the Kennedy Getting type. The Kennedy is for the press, Getting is for the fact that when we got to acquired this press from the chemistry department, Yvonne Getting was kind enough to come around and help us clean up the press and activate the pressure system so we could use it, and then we installed the Walker type module inside there. So we guess we should call it the Kennedy Getting Walker apparatus. And this is Baosheng having learned how to measure the sound velocities using the Jackson interferometry techniques in some of his specimens. In fact, the most recent collaboration between us and Stony Brook, one of Baosheng's other students, Ting Chen, measured the sound velocities of polycrystalline cosite at high pressure and temperature using a specimen that I had hot pressed in a girdle anvil apparatus in 1975, and for whatever reasons, I still had it. So the people in the laboratory like to say this was a well-aged polycrystalline specimen. Her measurements were done in the last 10 years. Next slide, please. Of course, that wasn't the only kind of apparatus we incorporated and acquired from the Japanese. One of the most prominent ones was a dia-type apparatus that was designed for us by Osamu Shimomura and Osamu Fukunaga in Japan as a model to their own apparatus in Tsukuba, which is called something -80. Now, max 80, excuse me, multi-anvil apparatus developed in 1980. So we bought one of those, and Charlie Pruitt and I had help from Shimomura and also Yoshiko Sato learning how to use it in the laboratory. And we were able to introduce other people, including Jean-Nic Anguin, postdoc from France, Anne Remsburg, one of my graduate students, and Gabriel Guanmisi using this apparatus. We called it SAM 85 because we bought it in 1985, and two of the people that helped us more than anything learn how to use it were Osamu Shimomura and Osamu Fukunaga. So the apparatus in Japan is max 80, the one in Stony Brook is SAM 85. And it has the distinct capability compared to the other kinds of multi-anvil apparatus that we've used for synthesis, that it has easy access to synchrotron radiation. And the next slide should show Don Widener and his colleague Mike Vaughn installing this apparatus, SAM 85, at the National Synchrotron Light Source at Brookhaven. You can see the anvil system in here consists of 6 anvils, 3 of which are shown next to Mike's finger, and they compress a cubic cell assembly into which you can introduce X-rays and acoustic signals and directly measure both the sound velocities of the materials, but also the structure, and just as importantly, the length of the specimen. So the next slide shows a schematic of what happens in this apparatus. So we've installed this dia-type apparatus at NSLS. This is the blow up of the anvil assemblies, showing these 6 anvils compressing the cubic sample assembly. The acoustic wave can travel from the transducer through one of the buffer rods into and out of the specimen. So you have an ultrasonic signal. At the same time, then in another direction, you have an X-ray signal coming in here from the NSLS and being diffracted. And, well, sorry, it's coming in from this side, beg your pardon. This is the X-ray diffracted along the 2 theta line into a solid state detector. So you have, if we can, I guess this, you can't blow this up very well, but the signal comes in from the anvil through a buffer rod into the sample and reflects at every interface, including the one with sodium chloride. The sodium chloride and boron nitride are used to create a pseudo-hydrostatic pressure environment around the sample, which we think is pretty important. Next slide. Looks like I'm running ahead of time, Tsuno-sensei. This is a summary of many years ago, or 10 years ago, of what these various experiments could do at various pressures and temperatures. If you look along the vertical axis, resonant ultrasound spectroscopy can measure to very high temperatures, most frequently at room pressure. The Brillouin scattering techniques that were adopted and pioneered by Don Widener at Stony Brook can reach incredibly high pressures, most often at room temperature. They go well above 50 GPa. The gigahertz ultrasonics, which we've been using at Stony Brook and ANU to measure the sound velocities as a function of simultaneous pressure and temperature, can reach now temperatures above 1500 K and pressures in excess of 25 GPa. I think the next slide is a similar representation of that. So here's the current status of sound velocity measurements in multi-anvil apparatus at high P and T compared to what can be done by Brillouin spectroscopy and the resonant ultrasound. So the resonant ultrasound and the Brillouin scattering more than generously cover the pressure and temperature axes. And what is particularly important for the Earth and geophysics is the large volume pressure ultrasonic experiments reaching now on the above 1500 K and on the order of 25 GPa can reach pressures that are beginning to measure through the upper mantle and perhaps at some later time into the lower mantle of the Earth. I think these are depths up here. This must be the transition zone of the Earth at 400 to 660 kilometers, and then into the lower mantle. Next slide. Okay, I said I was going to dedicate this talk to Orson Anderson some years ago, actually 1971. If you'll excuse me, I need some water. I had the pleasure of introducing Orson at a workshop on seismic anisotropy that some of my colleagues in what was then Czechoslovakia convened at a castle in Liblice in 1971. And there were subsequent meetings in 76 and 81 and 86 and 91 and 96 at various places throughout the world. Next slide. All right, this is just a summary of the work that Jackson, Niesler, and Widener did to develop their ultrasonic interferometry. I think I've shown that one before. And this is also included in the abstract, which was distributed by ASU. The next slide. So I said I'm going to bring it up to date. And so I wanted to cite 2 studies that have been done in the last year, ironically on specimens of hematite that I loaned to these people, Ran Wang in Baosheng's laboratory, and a former postdoc, Gongtao Zhao, who is now back in Japan and co-authored a paper with Irafuna recently using some of our specimens. So I think the next slide is Ran Wang's measurements. Again, in a multi-anvil apparatus, so you have the transducer going through a tungsten carbide anvil into a buffer rod, reflecting at each interface off the sample and sodium chloride interface, and generating a series of echoes. Here's the P wave interface off the anvil, the buffer rod of alumina, the sample, same thing here for shear waves. And if you use a dual mode transducer, which we can now, you get, yes, go back one slide, please. You get, no, okay. You get both simultaneously the P wave and S wave signals, which allows you to measure in the next slide the velocities of compressional waves and shear waves up to 13 GPa, much, much higher than 0.3 GPa, which we measured when I was a graduate student, but on the same specimen or specimens from the same source. And if you convert those, of course, to bulk modulus and shear modulus, you see you can plot these as a function of pressure at room temperature. Now, hematite's a strange animal, so you have to be careful when you measure it. And that's revealed by a recent paper published in iScience by Yongtao Zhou, former postdoc at Stony Brook, working with Baosheng, but back in Japan now. Next slide, please. I think he's back in Japan. No, I beg your pardon. He's in China, of course. And this is his apparatus. Again, it looks like a dia-type configuration with a synchrotron X-ray generated here and detected the diffraction measured by the solid-state detector. The ultrasonic measurement system then different direction is measuring the acoustic travel times of both P and S waves, and they can be measured as a function of pressure. What's happening in my screen here? I don't want this. Okay. Whoops. Can you back up one? I lost it here. Do you still have my screen?
Yeah, we can still see your screen. What happened?
Are you seeing my screen now?
Yes.
Okay. Where was I? Okay, I had Anderson's lecture in Czechoslovakia. Then just a few photographs of Ed Schreiber and Orson visiting the diatremes of northeastern Arizona that we did that in 1960s. And then these recent studies of hematite that I think will show up in this is the measurements by Ran Wang in Baosheng's laboratory. Ironically, they used the same specimen that I used with Schreiber back in 1968. The compressional and shear waves versus pressure, and then converting to the bulk modulus and shear modulus. And this is the one recent paper by Zhou et al., including Irafuna. And the interesting thing, you have to be careful when you measure a hematite, because if you measure it as a function of pressure at room temperature, the compressional wave velocities are very smooth. But if you're not very careful, the shear wave velocities, which I only measured to 3 GPa, if you measure them beyond that, there's a kink. And there's a kink because at room temperature, at room pressure and about 98 K, there's a transition of hematite from weakly ferromagnetic to antiferromagnetic. Not a change in in cell volume just to change in the magnetism. And you can see that it puts a kink in the wave velocities for shear waves. Back in the late, this is called the Morin transition, and I studied it extensively with Shubert Banerjee from the Ampex Corporation back in the 1970s as a postdoc in Orson's laboratory. So it's okay to use old specimens. Just be careful what you do when you measure them into unknown regions of pressure and temperature. And I think that's my last slide. I apologize if I've either run over time or not used enough time. It's back to you, Tsuno.
Yeah, thank you, Bob. Actually, the timing is great, actually. So, guys, if you have any question, you can raise hand, and I can grant your permission to speak with Tom. So, if you have any question, raise the hand. Yes. Yeah, Marcus, you can talk.
Hi, Bob. Many thanks for this nice talk. I'm not much into velocity measurements. You mentioned the dependence of the sound velocity in this polycrystalline alumina, but there's also a pressure gradient inside the anvil. How about that?
Yes, that's true. We try to minimize that by surrounding the material, well, not the anvil, but the specimen with sodium chloride. But that you're correct. The anvil is not protected in that way, and there surely is some pressure gradient. I don't know off the top of my head how you correct for that. And thanks for the question. Who was this?
This is Marcus from Freiburg in Saxony, Germany.
Oh, good.
Yeah,
nice to
I
hear from
learned
you.
at BTI at Bayreuth.
Yes, guten Tag.
Hallo, guten Tag. Thanks.
Okay, so do you have any question? Okay, Professor Ian Jackson, you can speak.
I'd just like to chime in from Canberra in Australia. I enjoyed your presentation, Bob, and a nice overview of where ultrasonics has been for the last 50 years. Thanks very much.
Oh, that's very kind of you. Our collaboration with you, starting when you were a graduate student and extending to the subsequent interactions through Sally Rigdon and Jennifer Kung, has been a very important part of the development of our laboratory at Stony Brook, as well as making sure that our friendship continues over many years.
Thank you.
So, Sibor, you can talk.
Hi, Bob. This is Sibo. I'm at ASU. Nice to see you again. So, I was wondering, the hematite sample you're showing here, is that a natural sample or it's a hot press or synthesized sample?
No, these are hot press samples at room temperature, done in various laboratories. One of them was Transtech, one of them was Ampex Corporation that Banerjee used to work at. And these were all, they're probably best described in our earlier papers, and I can send them to you if you send me a note.
Sure. Thank you. Thank you, Bob.
Sure.
Let's talk.
There was one exception for that. A colleague named Shapiro in Philadelphia actually grew and loaned me a single crystal of hematite, very small one, and we were able to do some detailed work in different crystallographic directions across this Morin transition. So I think it's in one of the papers by Liebermann and Banerjee.
Got it. And this sample also used for that 0.3 GPa measurement. They're the same sample. Is that correct?
Well, if not the same sample from the same source and same collection.
Okay, I got it. Thank you.
I saved a lot of samples, but I can't be absolutely sure
I got
which
it.
ones were used.
Okay, thank you.
You're welcome.
Okay, Dan, Dan, you can talk.
Hello, can you hear me?
Yes.
Hi, Bob. This is Dan Shim. It is really, I'm glad that I can hear you and I can attend your talk today. And I really appreciate your historical perspective of this ultrasound technique in multi-anvil press, which has played an important role. And I also like to take this opportunity to, express my gratitude and on behalf of our community, all the contribution you have made. And particularly, I'd like to highlight the fact that you encourage us since 2014 when we try to establish this multi-anvil press national center, which now we call FORCE. And because of your encouragement and all those, work that you have done, we had community support, and now we have this beautiful presses. So that being said, I'd like to hear some suggestions from you. Now we have this two really unique presses in our facility, Ichiban, that is 6,000 ton press and a cubic press. And, we are very interested in implementing this ultrasound technique. What would be the area that we need to think about and take care of when we implement ultrasound technique to these new presses?
Well, I guess as a geophysicist, my primary interest would be in seeing you conduct these sound velocity measurements on a variety of different mantle materials, including some that might undergo phase transformations while you're doing the experiment, which probably stops the experiment because the sample will disintegrate, but might be very interesting. And of course, there must be interest in other materials that are concerned to material science rather than geoscience. But I would encourage you to use the fantastic opportunities made available by Baosheng and your other apparatus to explore different physical properties that can mirror what happens inside the Earth. And I must say that thank you for your comments about any influence I had in helping FORCE get started. You have really taken the baton for developing in the United States ultra high pressure, large volume apparatus that started previously at Stony Brook and then was part of Compress and Chipper, various activities that I was involved in. And clearly now the crown for these activities within the United States rests at ASU. So congratulations, Dan, to you and your colleagues for developing the apparatus and especially for making it and its resources available to the very wide high pressure, high temperature mineral physics community. Congratulations.
Thank you.
Okay, so it looks like there is an question from Dr. Ben Bergman. It looks like his microphone is broken, and so I will read his question. So related to Dan's question, so what are the limiting factors in terms of setting up ultrasonic at higher pressures? For example, above 25 GPa in a diet presses? That is a Ben's question. Bob, do you have an answer?
Well, I think the primary thing that limits going above circa 25 GPa is by the time you reach that pressure range, the sample is small, the confining medium is small, and the anvil tips are small, and you'll reach the point when a multi-anvil apparatus really becomes indistinguishable from a diamond anvil cell, in which case you better switch over to the Brillouin scattering techniques that my colleague Don Widener has been so influential in utilizing in geophysics. So I don't think you're going to, as the size of the apparatus and the specimen gets smaller, what you really have to do is go to higher and higher frequency waves, and at some point you're out of the ultrasonic range. So
Okay, we have still a few minutes. I think Marcus, you can speak.
Yeah, Bob, it's me again. Since there is a considerable community of multi-anvil people there, how many synchrotrons have angle dispersive XRD on the world? I'm often at ID06 at ESRF, and they really appreciate our special amorphous gasket materials I developed. And I really asked myself, I mean, they really still need improvement, because boron is usually not really amorphous. It also often has impurities, so it's appreciated there that there's nothing in the beam. And I would like to know if there would be an interest or a need for development of really low Z, high transparency gasket materials for all these purposes.
sounds like a good target. I'm retired. I'm retired. And I didn't mean not to mention the ESRF and other synchrotrons. I guess I was being a little bit domestic in saying the NSLS and APS.
Yeah, sure. But I'm just asking for a general need. I mean, if most people work at fixed angle and they say, okay, it's not necessary, we've got high enough brilliance, we will just hit our sample, and precision of the peaks is good enough to see most of the important structures, then there is no need. But if you go to angle dispersive, then it may be important.
Yes, yeah, you're right. I don't have any more guidance than agreeing with you.
Okay.
We have just one more minute. But if you don't have any, do you have any question? Maybe there isn't time for just one question. Okay, so
Zuno Sensei, could I interrupt and just use this minute to thank you and Kara Brugman and my other friends and colleagues at ASU for this invitation. I mentioned at the beginning that it's been more than a decade since I've given a professional talk, and I've used the last month or two while I'm living in this independent living community near Stony Brook to try to search my computer and find some slides that might be of interest to your community. So thank you again for the opportunity. It helped me to keep alive professionally a little bit longer. Thank you.
Yeah, thank you.
Bob?